So what is strength estimation? Strength estimation is the process of evaluating concrete's actual strength at various stages of construction. By doing this, it helps ensure the structure can safely support applied loads such as formwork removal, shoring, post-tensioning, and other construction activities. It also helps account for real curing conditions, which can differ significantly from a perfect ideal laboratory environment. Concrete strength is the governing parameter for many early stage construction operations, formwork removal, successive floor placement and construction, post-tensioning, reshoring. They all depend on achieving specified strength thresholds, which are normally or usually defined in the project specifications. Without accurate strength estimation, either construction is delayed unnecessarily or unsafe sequencing can occur. Over the years, several high-profile failures have occurred because loads were placed on concrete that had not yet achieved the necessary strength. And that's why accurate strength estimation ultimately protects workers, prevents structural instability, and it maintains adequate safety margins throughout the construction project. One of these failures is the collapse at 2000 Commonwealth Avenue in Boston in 1971. It's a classic example of what can happen when concrete is loaded before achieving sufficient strength. The building used flat slab construction, and the roof slab around one of the columns had not developed the required compressive strength because it wasn't protected um, during extremely cold weather. So at the time of failure, the concrete had only reached about 1900 to 2100 psi, which was far below the specified 3000 psi design strength and below the minimum needed before removing shoring. When the workers added fresh concrete for the mechanical room slab, along with other construction loads, including two other boilers stored on the roof, the slab just couldn't resist the punching shear forces. So the slab, unfortunately, suddenly dropped several inches and then failed, causing a rapid progressive collapse through multiple floors. Tragically, four workers were killed and two-thirds of the structure was destroyed. So this demonstrates why accurate in-place strength estimation is really essential before loading concrete or removing its shoring. Concrete compressive strength, it really is the cornerstone of the concrete design. ACI provisions and engineering models derive other mechanical properties such as the tensile strength, flexural strength, and the modulus of elasticity um, from the compressive strength. Confirming, the compressive strength in the field ensures the structure is achieving the minimum performance criteria assumed by the design. Concrete strength gain is a function of hydration, which we have learned throughout this course. It is influenced by both time and temperature. Higher temperatures accelerate hydration, while cold temperatures slow it significantly. Additionally, moisture conditions and curing methods in the field impact its actual strength gain as well. Lab cured specimens do not reflect real world curing. They are typically stored at constant temperatures and moisture levels. However, in contrast, concrete in the field undergoes the daily temperature cycles, wind exposure, and an inconsistent moisture, all of which affect strength gain differently. So, in other words, it's more representative of what the concrete will actually see throughout its life cycle than a specimen that's cured in the lab. Reliable strength estimation allows contractors to safely optimize their schedule. Instead of waiting fixed time intervals, real-time data enables construction to resume or continue as soon as the concrete reaches the specified required minimum strength. So all of this ultimately reduces the time lost and most importantly maintains safety on the project.